All right, buddy. I'm Zeke Fletcher.
I'm Tyler Kelly, and this is our report on the Common Lisp programming language.
So, just a brief history of Lisp. It was made in 1958 by a guy named John McCarthy while he was just doing some simple research at MIT. Um, Throughout the 70s and 80s, there were different kinds of projects being used with Lisp, and each developing their own dialect to meet their needs. In the 70s and 80s, during the 70s and 80s, we had a golden age that involved the usage of Lisp, and it was dominant for AI research. From this, a boom of the boom of Common Lisp emerged, and as we know, throughout later history, stuff like C++, Java would eventually overtake this. But at this time, like 70s and 80s, that was like Lisp's time.
So next up, we have the fundamentals of Common Lisp. So we got a lot of fundamentals to cover in here. So we're going to start off with the very basics. So within Lisp, everything, whether it be a function call, an expression, a string, integer, all takes place in atoms, in list. These right here will indicate a list. And inside these lists contain atoms. So this whole thing right here is called S expression, and they are either um sorry, S expressions consist of a list and atoms, but it can also be an empty list and still be a valid S expression. S expression really just refers to a list that may or may not contain atoms. So next up we have the paradigm of Common Lisp. It is both functional and object oriented, which is very similar to Python, where it is very function driven. Functions are data type, but at the same time, objects can be used heavily. So Common Lisp is multi-paradigm, as I said. Originally, like just Lisp, the original Lisp, no dialect, was only a functional language and had no object support. But in the 1980s, with the advent of Common Lisp, object-oriented programming was fully integrated into Lisp. This is done using the Common Lisp object system, which I'll talk about later. Here's an example of a function. As you can see, its syntax we'll explore later in the next section. But here's an example of a object declaration, or sorry, an object instantiation, which means that Common Lisp supports objects and functions, which leads to this multi-paradigm language. So next we have the scope of Lisp. As I mentioned before, everything takes place in these S expressions, which means that the scope is restricted to these S expressions. However, there are global variables, which I'll kind of point out later as we go, that will last outside of these X expressions. But unless it's a global variable, it can only exist within this scope. Meaning when these parentheses close, that disappears. It's no longer part of your code, no longer in the program or memory. Next part of Common Lisp is it is dynamically typed. Unlike languages like C++, where you must like hard declare a variable, like for C++, you might declare a variable like that, and it'll have the int keyword beforehand, meaning it's hard type. You need to remind the compiler, tell the compiler what data type you want to use, or if you want to return a function, or sorry, return a value from a function, the compiler needs to know what value to return, what data type to return. Whereas in Lisp, you'll see there's a very much a lack of any identifier. This is a global variable, really a global parameter. Kind of the same thing in Lisp. Def parameter, myvar2, myvar with the value 2. These stars indicate a global variable, but that's besides the point. What I'm getting at is there is no hint to the compiler as to what data type this is. It's interpreted on runtime, kinda. The reason I say that is because Common Lisp is a just-in-time compiled language, which sounds kind of weird because it's like a hybrid between interpreted and compiled. But what it means is that it goes through each line, compiles it, and then runs it like an interpreter. But if it finds a line before runtime that's repeated, it'll compile it and save it in memory to save time and space later. So it's actually really efficient and really flexible, which is a very cool thing about Common Lisp. Up next are expressions. So as I mentioned before, everything belongs as in an S expression, which itself is a type of expression. This means expressions are essentially the backbone of Common Lisp. There's no really executing in Common Lisp. Instead, you're only evaluating an expression. So to show this, here is like a C++ standard like pseudocode. You would literally just have code that gets executed that returns a value. Think of like the int name function, which returns -1 or 0 by default, however you set it. Whereas in Common Lisp, your entry point to a function is literally just an expression. Which on a technical level, that means when you run a script, a Common Lisp script, you're evaluating one large expression, whereas when you run a C++ script, you're running one big function, the main function, which returns a value. So the best way to kind of explain the syntax of expressions is to use mathematical expressions with Common Lisp. Um, because there is no need for return statements, it can often be confusing for a programmer trying to learn Common Lisp coming from something like C++ or from Python. So we found it was best to use math expressions to explain this concept. So This is gonna look really weird at first, but it does make a lot of sense. So we're gonna use just the simple plus, square root, and the star, which is multiplication operators, which are also functions in common Lisp, which I'll get into later, to demonstrate this. So we'll start over here. We have the operator in front, which is a plus, followed by argument one, argument two. So in math, this is the same thing. It evaluates this mathematically 1 plus 1, which equals 2. So let's say it again. Function name, argument 1, argument 2, 1 plus 1. And here's another example. This is kind of about nesting expressions because within Common Lisp, you're going to nest expressions. Nothing will get done without nesting expressions. Square root is function call number 1. Function call number 2 is plus. And then you have the innermost nest, the two arguments, 1 and 1. So what it evaluates to, I'll draw this over here to make it more clear, is nest 1, 1 plus 1, which equals 2. And then we have the square root of 2, right, which equals square root of 2. I pretty made a mistake on the slide and put 1 by accident. Square root of 2 is definitely not 1, it's definitely 2. But I digress. Thankfully, we have the marker to correct that. That is my bad. And for a final example, we'll do a really nested function. Square root of plus times 1, 1 times 1, 1, which sounds like a bunch of junk when you first read it, or when you look at it without understanding the syntax of Common Lisp, it makes no sense at all. But once again, I'll remind you, function name, terrible handwriting, name, arg1, arg whatever, like however many arguments you have. So here we see square root, the function, and the first argument of this function, or really the only argument of this function, is another expression, which is plus. And the two arguments of this plus expression are 1 times 1 and 1 times 1. So this mathematically evaluates to square root of 2, or square root of 1 times 1 plus 1 times 1, is what it looks like in mathematical expression. Finally, on to basic data types. And when I say basic, you'll understand when we get to advanced data types. It's a bit weird in Common Lisp. Numbers. So Common Lisp is actually really cool with numbers because they don't have just the basic integers, float, double. They also have ratios, which are really sick because you avoid rounding errors and you avoid repeating decimals, because Common Lisp will see that and say, oh, that's 1/3, which is very unique. I wish modern programming languages kept this around. Instead, if you want that effect, you create your own class or import a package in Python, which is really lame. But there are 4 basic numbers. Like, number itself is not a data type, but there are 4 data types that are part of the numbers family. Integer, very familiar, should be familiar with everyone. 1, 2, 3, 4, 5, whatever. Floating point, similar to a double in C++. It's just a get decimal. Ratio is really the ratio between any two numbers, but is best used for decimals that can't be represented. Like 3/5 is kind of a bad example because this can be 0.6. Probably should have used 1/3 there. Complex numbers, which are really weird. I don't know. I didn't even realize Common Lisp had the native complex support until I started this, which is strange. So you can actually represent using a complex function, which is built into Common Lisp. Represent complex numbers. So that's kind of neat, like 2 plus 5i. Booleans. Booleans are also strange in Common Lisp. Everything is strange in Common Lisp. So they don't store true or false. They actually store true or NIL. And NIL means not in list, empty list, or false. By default, every object or every piece of information in Lisp besides an empty list is identified as true. Meaning when it's passed into a conditional statement, if an object exists, it's true. Like, for example, this object right here, let's go triangle. In Lisp, a triangle is declared true because it exists. However, an empty list have the value of NIL or not in list. It's a little bit strange, but a bit more sensible to get into objects and how they work under the hood. So here's just an example of syntax of declaring a true variable. Def var, the word we saw that keyword before. Is valid means it's global. T, which is true in Common Lisp, is a symbol for true. Def val is empty, NIL, or def var is empty parentheses. Like I said before, this is the same thing as not in list or empty list. And evaluating it, like 3, just the integer 3 is true. Like I said, every object stores true inherently, and an empty list is false. Characters and strings. Characters are stored as ASCII values that are then converted using a table. However, there is still support for non-ASCII values, and they're stored into a extended character subclass of the character main class. So what I mean by that is within Common Lisp, most data types have sub-data types, and characters are no exception. So if you can't find your character value in an ASCII table, it extends and allows for crazy things like emojis, foreign characters, whatever. And strings are a 1D vector, which I'll cover in just a second. And string can be any length and consist of any characters. So here's declaring a simple character, and here's declaring a string. Very straightforward, very similar to most languages. Functions. It may seem out of place that functions are simple data types in Common Lisp, but this is what makes them so unique and powerful. Since they are data types, they are considered first-class objects, meaning they can be assigned to variables, passive arguments, returned from functions, and stored in data structures. Meaning, we can declare a function which has a syntax of defun, function name, parameter 1, parameter 2, parameter 3, function logic, as well as call the function with this syntax right here, and store the function in variables, or store the function in data structures. And this keyword here, setf, is very important, and you will see it more and more as we go on to the presentation. Setf actually stores a value into a variable itself. It changes or mutates the value of a variable instead of making a copy. Data structures, aka advanced data types. Arrays. Should be familiar with arrays. Arrays are general sequential memory containers in Common Lisp, and they can contain any data type for a specific length. However, they can be automatically resized with the adjustable T parameter, which I have an example right here. Yes. Adjustable T parameter just allows a compiler to automatically resize the arrays when pushing new values in. But in reality, when you apply this parameter, it becomes a vector, which we will talk about next. But here's the simple syntax for declaring an array. This is actually two-day right here, 3x2. This is inserting a value using the setf we talked about a second ago, and a new word, aref, which means access reference, or in this case, accessing an array, and returning the element. And so what this does is it sets the value at myArray to 1 to 99. Vectors, I talked about these before just a second ago. Vectors are a subclass, kind of like how extended character is a subclass of character, a subclass of Common Lisp. They are one-dimensional, restricted to one-dimensional, and they can resize automatically, and that's why string is built on them, so strings can be any length. They allow for indexing with aref, but they also have methods like push and pop. Here's declaring an array, but making it a vector with a make adjustable parameter I talked about a second ago. Vector push and accessing a vector. All the syntax for you right there. Then we have the list in Common Lisp, which is literally everywhere. Like every time you see this, that's a list. And this actually uses a linked list implementation, which should be familiar with linked list. Within list, they're actually called concells. They have the car and the CDR. The car holds the current position. The CDR points to the next item in the list. Here's a simple syntax for declaring a list. Def bar is once again declaring a variable that is global called myList, and it is storing a list of 1, 2, 3. List of 1, 2, 3. It's just a list of 1, 2, 3. Here's pushing a new element, and here's accessing a list, which is kind of weird because it uses a function called int, and you can put any value here, and it pretty much just goes to that value. Like int 6 would go to the 6th element, int 2 of my list would go to the 3rd element. Dictionaries / hash tables are kind of cool because they are built into Common Lisp, very similar to Python, unlike C++. Common Lisp hash tables use an array of buckets and linked list chaining to resolve collision. Because of the array implementation, they are really fast with over 1 time complexity. You declare a hash table using this syntax right here, as well as adding a value with this syntax right here, and retrieving the value, this syntax right here, and here's what kind of value is to at the bottom. Structs, aka junior objects. Structures or structs are a special kind of container available in Common Lisp. They are kind of like a custom data type. Here's an example: define struct person with the name, age, and height, and then you can define a new variable called guy and assign it a make person, which is the function to declare a strut. It's simply make dash the name of your strut. Name Tim, age 30, height 1.65. This will create a person strut with the attributes Tim, 30, and 1.65 height. One thing I will point out here is this kind of notation is quite similar or very common in Common Lisp. Breaking up your expressions kind of by spacing using these parentheses helps with clarity and reading overall, especially in the next section for object orientation. Objects using a Common Lisp object system, what it stands for. Classes are like blueprints that tells the compiler how to create an object and what methods belong to each object. Floss, of course, uses these powerful blueprints to build complex objects. Here's an example of a class called def class person. Here are its members right here. And then we have a method that belongs to the person class that will print it. I'm not going to go line by line on this because we've already covered most of these concepts, but feel free to pause the video and go line by line just to get a feel of the person class. Slide. So here's how we could create an instance of the person class. Def var p1, which is a global variable, make instance person, name Alice. So we're saying we want a person with the name Alice, or right here, we're going to come here, we're going to set f, which is a keyword I mentioned earlier, which means we're going to actually change the value from person name, which means we're going to access our person object, access its name of the variable p1, which is this guy up here, and change its name to Bob, which is how we can mutate objects. Now, next we have inheritance, which is very, very simple in Common Lisp. It's literally def class child, or make a class called child. It's going to inherit a person. And then within that class, we're going to add favorite toy. And this class will have, oh, sorry, one more thing to hit. Init form is default arguments for a class, or default values for a member. My apologies. And for this, in this case, bouncy ball is the default toy for a child. That means that the child class will now inherit all the traits of a person, plus having a favorite toy, as well as the accessor for the favorite toy, which is called kids toy, and the initial value. Control flow. Within Common Lisp, we have conditionals, which may look a bit different than most programming languages. For example, this one's true when x is greater than 0. We kind of covered this section already when we did mathematical expressions. Here's a list, ironically, a list of common conditionals with a symbol on the left, the meaning in the middle, and the example on the right. You'll notice a common pattern. The operator always comes in front, followed by the argument, because once again, these are technically functions, because everything's a function, and an object at the same time. Welcome to Common Lisp. Next up are logical operators. They work with the conditional operators. They are used to create powerful and complex conditional statements. When combined with conditional operators from before, Common Lisp has 4 built-in logical operators and or not and null. Yeah. So, and or not null, as I said. So the purpose is for and, you know, this true when one value are true, or true when one value is true, not true when one value is false, true when value is empty. Here's a usage. Like I said, T from the Boolean section is true in Common Lisp, and true is true or not true, or empty list is true. Not one is less than 0, which is true, and not empty list, which is true. Or sorry, null is an empty list, which is true. It evaluates to true. Conditional control statements. Conditionals traditionally belong to control statements. Common Lisp has several conditional control statements: if, when, unless, in case, / e case. Here's the basic syntax for if, when, in case. So I'm going to break them down more in this section thoroughly. So we have if starts here, then we have the conditional statement right here in the yellow. And then we have the positive logic, meaning if it's true, it'll evaluate to this. And then we have the negative logic, meaning if else, if the conditional is not true, we're going to print the negative logic. And you'll see this is very different from every programming language ever, because there is no else keyword. If you want to create an else if chain, you continue to nest more and more expressions inside of this negative expression, which it's a thought. It is a Common Lisp. Next is when. When may seem like it's a loop, but it's not. It's just an if statement without negative logic, meaning when the conditional is true, execute. If it's not true, it just moves on and skips the expression entirely. Next, we have case, which is like the switch statement in C++ and match statement in Python. Take a case, if matches the key, execute the value. And otherwise, if there's no match, it goes to the default value. Next, we have loops. Second main form of control flow is loops. Comment 3. First off, with the loop keyword, go figure. Loop for iterator value from lower to upper do logic to be repeated, meaning here's an example. For the iterator value, which is k, this is a variable to be clear. For k from 1 to 5, so it goes from the number 0, 1, 2, 3, 4, 5. Do, what's it going to do when it happens? It's going to do the positive logic, which is print k, or in this case, it's going to print 1, 2, 3, 4, 5 to console. An important note is that this starts at 1 and goes to 5. It's inclusive. Do times is a simpler version of the loop, which does this from the iterator variable to the upper bound, do this logic. So in this case, it does start at 0 and it's not inclusive to 5. It's just a simpler loop, which has its own use cases. Next up is mapcar, which is a built-in loop function of Common Lisp, which applies a function to every value or every element in a list. For example, this is an anonymous function, lambda function, which multiplies the value by 10. So it applies this function to every value on this list, creating 10, 20, 30, 40, 50, and it updates the list itself.
Okay, evaluation. And everyone knows this is the Sylvester criteria. You all know what that is. I'm just going to say that for every dot, this first dot is readability, the second dot is writability, and the third dot is reliability. Okay, so everyone should know that. So with control structures, they're super recursive, which is not good for debugging because you have the same thing. You have parentheses on parentheses. It's very hard to read, and it's very easy to get caught up in this mess. But when it comes to loop and map card functions, those improve writability once you learn because they enhance a lot of your programming. And when it comes to recursion, again, if it's improper, you have a higher chance of a stack overflow, which is not good. Data types. There is a heavy reliance on lists in Lisp that can obscure the language and make it difficult to understand for newer users. It's flexible, which creates fast prototyping, and you don't need to declare structures up front, which this overall accelerates development of your programming, and lacks compile time type checking, which can create runtime errors. Like, for example, you could expect a string, yet you could get a list instead, which is not good. Syntax design, it's very simple syntax. So while it's easy to like mess with, it's very easy to get lost because once again, parentheses are a lot of them. It's very easy to mess that up. You can actually put one and this syntax, but while on the flip side, this syntax makes it easier to create programs that can manipulate other programs, which is super useful. And this structure is very syntactical and uniform, and so it's easier for compilers and parsers all the way around. Support for abstraction, higher order functions are like, I mean, that's just hard for any newer user to anything, a higher function. Powerful macros, which can help developers create abstractions that can reduce repetitive code, and these well-designed abstractions can overall reduce bugs. Expressivity. Expressive code represents complex logic, which can be obscure, and but at the same time, complex logic, like those big functions, can do a lot and control the flow of the overall program. Concise problem expression, this can create concise problem expression, especially with math and data. Compact writing means fewer lines and bugs, yet it's hard to debug expressive one-liners because once again, they're all dumped together. Crap. Type checking. Types aren't directly declared, like Tyler said. You put var next to your variable, or you put int or float or double. You don't do that in Lisp. So this is once again confusing. You know, it must be learned in context whenever you're making the whatever the heck you're making. Dynamic typing is easier and faster because you don't have to do that, but at the same time, just know what you're talking about. And since types are checked at runtime, it's hard to see bugs because usually, like if you're in C++ and you type around, you'll see an error with your variables and stuff. But that doesn't happen, and so naturally once it's run, you'll then see the error. So it's very hard for you to know you have an error until you actually run it without taking extensive time to go over this. Exception handling, Lisp checking is very verbose yet super powerful. Error recovery is significant when dealing with normal logic. Catch and handle exceptions vary in a certain way, or catch and handle exceptions in a certain way. Restart computations and define custom conditions are all super complex, but way more effective than C++ to try and catch function. And there's also flexibility in error handling. Uh, Restricted aliasing. I don't know how to say that word. It's very hard to follow code in any language, and Lisp has immutable data, making code easier to follow, easier to write code without pointers, which is just an objective fact, and less worrying about aliasing. How you say that? But recursion and immutability generates side effects-free logic, which allows for easier tests. And just no pointers can create stability in your program, and it's a lot less likely that you'll make an error with this.
All right, so I'm going to briefly go over our medium code notation. So we did a 8 puzzle solver. So essentially what that is I'm sure you're familiar with the kids game, the 8 puzzle where you slide the pieces around and you try to get the numbers in order. We essentially implemented a searching algorithm that solves a 8-bit puzzle in Common Lisp. So I'm going to quickly go over how the code itself actually works. So there's 6 steps we got to create, or 6 functions we got to create when we run the code. We need to store the puzzle and display it, a way to swap tiles, a way to generate possible actions, a way to evaluate the cost of taking an action, a way to check the board as a goal board, and a way to print out the solution. So step one, boards will be represented with a 2D list right there. The board to the left of the goal state, for an example, that's what we're trying to solve, what we're trying to get to. Step one continued, we also need a way to print these, and this is a simple print function. This is a format. I don't really speak about this. There's another built-in list function similar to the print function. It's a formatted print, meaning we have more control over what actually gets printed, and we can print variables themselves. This function right here is designed to do exactly that. Another step two, we need a way to swap tiles. I'm actually going to cover the algorithm that we use for solving in the slides here because that's more of a algorithmic design instead of a common list thing. But I will kind of go over a little bit of syntax here. Here we see the map card function we kind of spoke about recently, as well as the int function and the setf function, which of course changes the value to new state. All these comments here, feel free to pause and read more in depth. And step three, we need a way to generate all the possible moves. And in here we use a loop with a nested loop with a do and a win, which is a bit of a nightmare to read. Like Zeke said, it's not super easy to follow code, especially in Common Lisp if you're not tuned to seeing Common Lisp code, which is why I left 1,000,001 comments in this section so this code can be read easily. Next, we actual function to generate the successors instead of just the possible moves, because we had a function that showed us the possible moves, but now we need a way to find the actual assessing states. That is essentially what this function does, using a combination of push, win, push, win, push. Essentially, if a move is valid, it pushes a state to possible states. Step four, if we want to find the best action to take, there needs to be a way to evaluate the cost of a function. For that, we're going to use a heuristic function Manhattan distance, which is essentially if you have two squares, this would be square 3, and this would be square 7, and 7 supposed to be where 3 is, 3 supposed to be where 7 is. We'd say how many spots does it take to get there? 1, 2, 3, meaning the Manhattan distance from 7 to 3 itself is 3. So this is a simple program right here, simple function that does that. In step five, we have a way to check the goal state is the state we're searching for, i.e. the solved puzzle. When equal, which is the operator I spoke about previously in the initial section, state and goal state, which are both 2D list. If they are equal, then we print solution found and print the solution path. And now we're going to need a way to print our solution, which is step six, is a simple function right here, which simply goes through each element that it took to get to the, each state that it took to get to the goal state, and prints them out. Now, ASR search itself, like I said, we won't particularly be covering in this presentation because it's more of an algorithmic design problem than an actual common list problem itself. However, there are plenty of comments in the code if you would like to go back and look at those. And here is the actual ASR function itself. Once again, I'm not going to cover this in here, but here's the code for it if you'd like to explore it. Anyways, now we're going to move on to a demo of our program.
All right, now we're going to move on to our live demo. So here I have the code pulled up in VS Code, and we are using the still compiler for Common Lisp to run this code. So I'm going to come down here and see that our start state, or the state we're passing into the function here, is actually going to go ahead and be 631, sorry, 402. I'll kind of highlight that right there. That's essentially the starting grid, the starting 8-bit puzzle. So we're going to come up here, and I'm going to pull up the output so we can see it a bit better. Press run, and here's what we got. So it starts off with just printing out our start state, which you see here, 634027885, and once again, here it is. And then it prints solution found, and it's going to print the solution path. So what's cool is here you'll be able to see what moves it actually makes. Like, for example, the first move is to switch to the empty spot, which is 0 and 4. And then it switches 0 and 6. And then we go down here, we switch 0 and 3. We kind of see the 0, this empty square moving throughout to kind of represent swaps happening. And then, and of course, finally we have the 8-bit puzzle solved, or the goal state. And we'll go ahead and just make it a bit more complicated. We'll switch up the grid a bit. We'll put the 0 here. Put the 8 here. 5, 0. And why not put 0, 2. So it's kind of like the essential. We just kind of re-scrambled the grid and we run the program again. And once again, solution found. This time it took 14 steps as opposed to 11 before. And as I scroll, you can kind of see the solving happening. And sure enough, we get right back to the goal state. So thank you for watching. It's been our live demo, and I appreciate your time.